All right, everyone, welcome back. Today's lecture, we're going to be talking about binary search trees. We introduced binary trees last week, but now we're going to introduce a more specialized binary tree. So, what is a binary search tree? A binary tree where values have an order, and the specific order um, takes advantage of the fact that trees are nonlinear, and so it gives us the ability to search for things more rapidly than if we had to go and do like a linear search, right? What's going to end up happening is we're going to be able to search for data in this binary search tree in log n time, right? And log is way better than n time, right? Which is what you would get from a linear data structure. But because you have to order these things in this binary search tree, then that's where that last bullet comes in. All data in the tree must be comparable. So you got to have some way to be able to compare the data to one another in the tree. So here are the kind of traits of our BST. And we can jump straight to the rules here, but we store items in our tree in such a way that finding the value we're looking for is going to be quicker in the best case. Here are the rules. The entry in node n, so whatever node you're at, we're calling it n, is never less than an entry in its left subtree. Now it can be equal, but we're not going to let it be less than. Okay? And an entry in node n is less than every entry in its right subtree. Or another way of saying is every entry in the right subtree is greater than whatever is at node n. Okay, so that kind of helps to establish these general rules. So here's an example of a BST. Now, one thing to note right off the bat, where this is actually what is this, a full or a complete tree? Right, so this does look complete in terms of how the different depth levels are filled in, but that's not what makes this a binary search tree. What makes this a binary search tree is that it follows these storage rules. The storage rules being that the entry node n is never less than an entry in the left subtree. So if we look here, so this 9, everything in its left subtree is less than 9. Everything in the right is greater than. Here, this 46, everything to the left of it is less than. Everything to the right is greater than. What about this 53? Oh, it starts to get a little weight. There's a 53 here. But again, the left subtree can be less than or equal to n, but everything in the right has to be greater than n. Okay, so here are 4 quick BSTs, we think, which are actually BSTs, right? Some of these are not, some of them are. What is not. Let's, you know what? Let's do this. I'm going to go ahead and drop this into my OneNote. So, number 1, this is not a BST, right? Because look at the left subtree of 21. Is everything on the left less than 21 or equal to? No. So that won't work. Let's check number 2. Number 2 is also no. Why? Well, let's see. Is everything to the left of 30 less than or equal to 30? That looks good. Well, what about, let's look at this smaller subtree. Everything to the left of 15 less than or equal to 15? Yes. But what about this 7? No, this has to be greater than 15. So it is not a BST. Okay. What about number 3? Number 3, negative. Right off the bat, we see on the left subtree of 5, we have a 22. That's not allowed. Yeah, I guess that's really the biggest thing right there that prevents it, because actually that 40 to the right of 5 is good. And then the children of 22, 19, and 24, those are arranged properly, but here's our mistake right away. Therefore, well, I had to give you one that was good, right? This one checks off all the boxes, right? We see this subtree is less than or equal to 10. This is greater than 10. Here for the 6, less than, greater than, we're all good. Let me ask you this question. What if this 8 was a 14. Would that work? No, right? Why wouldn't that work? Because 14 is greater than 10, even though it's 14 is greater than 6, so it obeys it to the right subtree of 6, it's greater. If we look at 10, that no longer works. All right. So I think that's pretty good so far. How about if instead of this being a 14, this was a 10? That would still work, right? Because then everything in the left subtree of this node is still less than or equal to 10. A 10 being there, that is all good. All right. So to build a binary search tree, we're going to use our binary tree nodes, our BT nodes. And on top of that, we got to have a way to insert the nodes, delete the nodes, etc. And we have to think about where we want to insert these nodes, right? Because there's these rules that have to be followed. So we just can't add stuff willy-nilly to this BST. We have to place the nodes in the correct spot. And when you delete, that actually becomes a little bit more complicated, right? Because if you delete something within the tree, like that's attached and has children's, well, some rearranging may need to occur in order to keep the BST a BST, right? You can't just take it out of there and reattach it and hope everything works out okay. You have to check, hey, do these rules still make sense? So what about inserting a new node? There's two situations we can think of. If you have an empty tree, it's kind of easy. It's going to be the first node in that empty tree. So therefore, we allocate memory using the new keyword, BT node item entry, and assign it root pointer. So easy. But what about a non-empty tree? Ooh, that was hard to say. Non-empty tree. And we want to throw in a new node. What do? Order has to be maintained. Let's look over here. Where would we add our 16? Now, let me tell you what it feels like, at least when I was first learning this stuff, where it feels like this 16 should go, especially coming from binary trees, right? You might feel tempted to say, all right, well, got to throw in a 16. Looks like I can throw in a 16 right here. But this breaks the rules. What's the rule? 16 is greater than 9. So here, this left subtree of 9 has to be less than or equal to 9. That 16 breaks that rule. So that's not the correct spot for that value. Where is the correct spot instead? Go ahead, point at the screen. I can't watch you, but point where you think it's going to be. Yes, that's right. All of you got it correct this time. I know it. I have full confidence. Now, see what I mean? This isn't a complete tree, and that's okay. We don't care about trees being complete or full. We care about these nodes being found in the correct spot. In fact, later on, we'll learn that depending on how you insert things into the BST, they might actually not really resemble a tree anymore, but that will be a little bit later. Okay, so that's where our 16 would go, because now all those rules are maintained, right? Everything, first of all, 16, we hit this 46. Where should we go, left or right? Well, 16 is less than 46, so you go to this 9. And now is 16 less than or equal to 9? No, it's greater than, so we got to go to the 17. So should we go to the left or to the right of 17? We got to go to the left. This was null, so that's where the node went. And me using that kind of a language, that kind of a logic, that's going to inform us later on when we have to write our insert function. Actually, I'll be honest, I give you the code for the insert function later on in the slide, so just stick around, but we'll continue to talk about how it should work. All right, now let's try a different value. Let's say we want to insert a 5. Let's go through that same logic again. So 5. Okay, to the left or to the right? It's got to go to the left. It's less than 46. To the left or to the right? Well, it's less than 9, so it's got to go here. 5 less than equal to 3? No, greater than. So we go here. There is nothing here. Therefore, that is the correct spot for our 5. All right. So that's how that goes. Now let's look at starting a tree from scratch. Say we wanted to create the tree as such. What would this final tree look like? So this will be important. This may be something you'll need to be able to do for the final exam. So let's run through it. Here we go. Here we go. I'm always afraid that I'm not actually recording. I'm like, oh no, I just talked for like half an hour and I wasn't recording anything. But so far, so good. How am I going to do this? How am I going to do this? You know what? I'll rewrite the instruction. And then, oh, you know what? No, I will copy and paste the instruction. So first thing. So insert 23. I'm going to go ahead and do that. There's nothing else here. So here's our 23. Now, insert 55. So I'll go ahead and drop this here. So this is where it's going to get a little bit interesting. But luckily, I have technology to help. So I kind of want to keep working with the same tree. So where should the 55 go? To the left or to the right? It's got to go to the right. And so here comes 55. Cool. All right. So let's copy this. Let's paste. This might not be the best way to organize it, everyone, but that's okay. I think we'll figure it out. And again, I'll upload this at the end of the lecture, so you will have access to this. No problem. So now we want to insert a 2. To the left of 23 or to the right, it's got to go to the left. So we've got our 2 there. Okay, and next we have to insert a 5. I'm just going to keep pasting and moving on down. Hope everyone's enjoying their, well, I guess whatever day you are working on this. For me, Sunday. It's been nice weather outside. Been getting out for a socially distant walk with the dog, so that's been good. I encourage you to do the same. So insert 5. Okay, so 5 has to go to the left of the 23. Then we hit this 2. It has to go to the right of 2 because it's greater than 2. So this 5 happens to fall there. Okay, 3 more nodes to insert. So let's grab this insert 10. Paste it there. Let's grab this and figure out where that 10 needs to go. Oh, did I not get enough? I think I missed some of it. That feels better. Okay, so where should this 10 go? Well, it's got to be to the left of 23, to the right of 2, and to the right of 5. See how it already has this like kind of weird structure? It doesn't look that much like a tree, but tree? Did I say tree? Hopefully I said 3. 3, tree. I knew it. I'm saying 3 instead of tree. Okay, forget that. It looks weird. It doesn't look like the tree we're kind of used to seeing from the other ones, but that's okay. That's how this works. Maybe later we'll have to learn about how to rebalance a tree, but that won't be for this lecture. That'll be for another day. Let's take this insert 34 because we're almost done. Maybe we can make this look a little leafier, make it look more like a tree before we're out of here. Okay, insert 34. Actually, I'm going to have to shuffle some stuff, right? So this 34 has to go to the right of 23, but to the left of 55. Actually, let's squeeze it in there. Okay, so that's in the correct spot, although it's a little bit tight, but that's okay. Last thing we have to do is we need to insert our 15. Maybe you've already figured that out. Maybe you did this on your own already and just are verifying your work. If so, kudos to you. I am 15. Well, it's got to be to the left of 23, to the right of 2, to the right of 5, and to the right of 10. Here is our 15. Weird, but that's how it goes. This is the correct tree that results from inserting these nodes in this particular order, right? Now, don't be tempted right now to do something like, well, this doesn't seem the most optimal, right? Like I could go in here and be like, well, what's the middle number here? Let's see. So there's a 2 and a 5, 55 and 34, to like maybe a 15, right? You might be tempted to say 15. All right. And then what we should get after the 15? Maybe a 34, a 23, and a 55. And then over here in the 15, maybe you go with a 5, a 10, and a 2. This is certainly a better balanced tree. It is probably an optimal tree. But that's not how these particular values were inserted into our BST. So we can't do this, not yet, okay? So don't feel tempted like you want to go ahead and rearrange it to be optimal. These are the same values in different BSTs, right? One that's laid out more optimally than the other. So we'll talk more about that later. Don't get hung up on trying to make it the most optimal. Instead, focus this week on just making sure all the rules are followed and that you are truly creating a binary search tree. Okay, let's get back to the lecture slides. So steps to insert a value, travel down the tree, checking the values of the node. Go left if the value is smaller or equal to, go right if it's bigger, stop before reaching null. So I've been stopping at null because that's where I insert our node, at least in the drawing. But when you're doing this in code, you got to stop before you hit null because you kind of have to have a pointer to the previous node in order to link it up to this new node, right? So go ahead and think about, just contemplate it for a minute or two, how you might do this. Again, I'm going to give you this code in a couple of slides, so don't worry too much about it. But I will go through the code as well with you so we can figure that out together. All right. But I think for our purposes, knowing the algorithm is much more important than being able to come up with the code. I mean, the code, you can look it up. Again, I'm going to give it to you, and I'll have another function where I'll kind of want you to write it using code. But just understanding how it works, how a BST works, super important. That's what I'm really interested in you kind of going through and understanding today. What about this removal of nodes from our tree? This ends up being a little bit more complicated. Okay, so what we do is we break it up into two functions. We'll find the target using a recursive function, and we're going to call that BST remove. And then we remove the target which we found using BST remove. And what we'll do is we'll call something called BST remove max. So move the next biggest node in the root's left subtree to become the root, right? So that is super, 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 super important. For example, if we go back to this example, let's say I wanted to remove this 46. Okay, and now, let's take this. And there's different implementations. I'm following the implementation most closely tied with our textbook, but it works. It works well. So it says, hey, let's say I wanted to remove this 46, because that's actually the most, like, removing a 3, 17, 53, 56, very easy, not too difficult, right? They don't have any subtree, so job is very easy. 9 and 23, little bit harder, but not too much harder because their subtrees just consist of one node. But let's look at the 46, which would be more like a real BST example where it's got large subtrees, right? What would make the most sense? So what we're saying here is, if we want to remove a 46, the idea is let's go look at its left subtree and let's go find the biggest number in that left subtree. So it's the 17, right? So what I'll do is I will go ahead and basically take this 17 and have it become the new root. And because it's the largest value in the left subtree, the rule should still be maintained. Everything else in that left subtree should be less than or equal to, and everything in the right subtree should still be greater than. We should still have a BST with the minimal amount of work. So that's kind of what we're working with now. Let's look at some prototypes. So we'll have a bool BST remove. So it just tells us true if it was able to remove that value, false if it didn't. A reason why it wouldn't is if it's not in there, it doesn't exist, right? So it takes two parameters, a reference to a pointer of BT node to the root pointer. And again, we call this thing recursively. So every subtree will have its own root pointer. And then we have also the target, what we're looking for. We also have a void BST remove max that gets called if we find the item, where we also pass in the root pointer. And this time, what we're looking to actually remove, right? And it's passed in as a reference because ultimately it's going to overwrite that root. So let's look at how it all breaks down. So if our tree is empty, we don't need to do anything, all right? So what is that going to look like? Let me take this and actually drop it into so you'll need to write this for the yeah, you know what? Let's grab it one piece at a time. So BST remove function. That's what we'll write down right now. BST remove function. So the first step we're saying is, hey, if the tree is empty, don't do anything. All right, well, that should be kind of straightforward to write a line of code for. So if the root pointer is what? That's right, null. If it's null, no, I can't do that. It feels like I'm on some PBS show. Oh, that's right, guys. If the root pointer is null, then return false. Right? You didn't remove anything because the thing is empty, so nothing to do. If the target is less than the root, call BST remove on the left subtree. So here's our recursive call. Let's grab that. Paste it. All right. So what might that look like? So if target is less than, now it's not root, right? Root's just a pointer, so you need to use the arrow member selection operator to look at its data and check that. So if the target is less than root data, then what do we have to do? We need to call that function recursively, and it's a recursive function call. So as part of the return statement, we will call BST remove on the left subtree. So we'll go ahead and say root left. And don't forget what we're looking for here is called target. All right, so far nothing's getting removed. We're just kind of trying to find what we're trying to remove. Let's grab this step here. If the target is greater than the root, call BST remove on the right subtree. Okay, let's paste that. So, I mean, can I cheat? Sometimes I like to cheat and just copy my other lines of code. Something I could never do on the whiteboard and always wish I could. All right, let's do this. If the target is greater than root, oh no, I lost some stuff. There you go. Root data. Then we need to call BST remove on the right. Oops, hit the wrong button. Awesome. Okay, step 4. So step 4 becomes a little bit more complicated because now you've found it, right? So let's grab this first one. If the target equals the root, so we'll throw that in an if statement, no big deal. We can do that. We can handle that. We are CSS2B students. We could totally do that. Let's write that in there. So if the target is equal to the root, but again, root's just a pointer. You want the data. Here's another condition too. If there is no left subtree, so let's just make that an and root root left is null. Yeah, that sounds good, right? And root left is equal to null. Then remove this node, making the right child be the new node. So that's a little bit funky. So it sounds a little bit confusing. Let's try to clarify this. This is what's going on. So let's say that there is a tree that kind of looks like this. It's a BST. And let's say what you're trying to do is you want to remove this 16 right there, right? And again, we want to basically remove these 16. So what this is saying is if the target equals a root, all right, so here we are, and there is no left subtree, right? So this is null. There is no left subtree, right? This is absent. Then remove this node, making the right child be the new root. So the right child is this 25. So it's saying make this 25 basically be 16. What ends up happening is that this gets attached to that 15. We end up getting rid of that 16, which is what we want to do anyway. And then the tree kind of looks like, let me see if I can grab this and redraw it by removing the links needed. Oh, up there, huh? It's not what I asked for, but such is life. So that goes away, that goes away, that goes away, that goes away, go away, goes away. And this 25, 2030 is now attached to 15, right? So that's what this means. If there is no left subtree, remove this node, making the right child be the new root. Right child is now the new root. It replaced that 16. But how do we do that with some code? Well, you want to declare a brand new pointer to kind of keep track of all this. I don't think we have that anywhere, so let's bring back, this is the color we've been using to write our code, right? So, no big deal. Let's declare a new pointer temporarily. So BT node item, we'll call it old. Previous, that's fine. And in fact, why don't we set the root equal to this? So now they're both pointed to the same one. Then you make sure that root is now equal to root right. So that's how we've advanced that. Then we go ahead and delete old. And then you want to make sure you decrement the node count. Oh, that looks like an equals, not a minus minus. And then you can return true. Right? And the reason this works so well is if you recall that originally when we are working with BST remove, this stuff is being passed as a reference. So updating the root pointer that way, right here, root equals root arrow right, actually changes the original root that this was invoked with, right? Because it's passed in as a reference to a pointer. So kind of interesting the way that works. But that's only half of step 4. There's another, right? What happens if the left subtree is not null? Otherwise, we call BST remove max on the left subtree. We will be finding the max value in that subtree and replacing the target with its value. If the root pointer's right child is null, We can store its data in the node that needs to be removed, store the root pointer's address, replace the root pointer's address with the address of the left child, and finally delete the. So honestly, that, like, if you break down that paragraph, each sentence, each part is a line of code, and we can do that, or we can mostly do that. Do we want to do the whole thing? What's kind of going on is it's saying, okay, so the left is not null. So first go left, and then go right until you hit null. If you do that, you're going to find the largest value in that left subtree, and then you'll have what you need in order to oh shoot, lost my train of thought. In order to replace the value you're trying to remove. Okay, so I mean, if you'd like, you can right. So all of these have been if statements. Oh, let me go ahead and close this if statement. Let me grab this. Actually, let's call it on this part here, right? That looks good. Paste there. So this can be inside an else, or you could just have it after all these ifs. All the other if statements have a return value. I don't know if you've noticed. That means that basically you could put this in an else, or you could just leave it outside. I think in my version, I just have it outside any if statement, because if you make it to this point, that means all the other ifs were false anyway. So no big deal. So we're saying first go left. And then we're passing in the root pointer data. And again, this is being passed by reference, right? If you look at the prototype for BST remove max, and the only way we get here is if we actually found it, right? And then this would end the entire function. But now it's all about the BST remove max function. Okay, let me make sure I'm not skipping any important steps here. BST remove max. So how much of that do we want to implement? Let me see. I want to give you some fun stuff to do during the lab. Reason for y'all to reach out to me and ask for help. Otherwise, I don't get to hear from you guys, and it's not as fun teaching this class when I don't get to talk to my students. So I'll work through some of this. Okay, BST movement. I won't leave you totally hanging, right? Maybe you just can meet, maybe you want to get together for the hangouts. Not the hangouts. We've been using the Zoom. Zoom's worked out super well. But I won't leave you hanging if you can't make it. I'm not that hurt. Just a little bit hurt. Okay. So what we're saying is you got to keep going right. So because eventually, if we keep going right, that's always going to represent the larger value, right? Because the right subtree is always the bigger, holds the bigger values. Oh, and here it's called root pointer. Oh, you know what? All the other ones, I wrote root. It probably should say root _ PTR. That's okay. You can make those edits. Especially if you've been following along, you probably already have made those edits. And I realized Mr. C messed that up. So if we look at right and it's null, that means that you have basically found, oh, and this isn't the color I've been using. That's okay. Easy to change. There we go. Life is good. Okay. So now, basically, we know what we have to overwrite, all right? And it's passed by reference. So again, awesome. We can say, take the root pointer's data, right? So the original value that we want to overwrite is here, but we just found basically the largest value in that right subtree. So now I'm able to overwrite it. Okay. And then what I want to do is I want to follow the rest of that. Store the root pointer's address. So that's this step. Okay, and then what does it say in the next part? Replace the root pointer's address with the address of its left child. So we'll say now link left subtree to root. Then it says delete the original. Delete the old root pointer, right? The one that you stored up here. This is where you want to delete it. Let me highlight those. So this thing that you stored, now you can call delete on it. Otherwise, you haven't gotten to the rightmost node. So no big deal. You will call BST remove max with root pointer right, comma remove. Fun stuff. Fun stuff. Oh, I won't lie. This definitely takes a bit to really understand and to grab a hold of and really own and make it your own and not be intimidated by what's going on. So take your time, ask questions if needed, discussions, Zoom meetings, whatever you'd like. But that gives you most of the code you need in order to work through the lab. Okay. So let's look at our revised BST remove. So here's entry 46. Let's say I wanted to remove this 46. So first thing I do is I shoot left. I find a 9. And then I have to keep going right until I hit null. So over here I go right. And I find 17. And there is no more right. So I know that 17 is going to have to become the new root. So 17 goes up here and replaces that 46. And then I can delete this 17. And I maintain a BST, a binary search tree. Everything is good to go. Okay. Gosh, I keep, old habits die hard. I keep wanting to be like, are there any questions on that? But no one's listening live. Maybe I should have some of these live recorded and then uploaded after. Again, this has all been a learning process for a lot of us. So we're still working through it, trying to do our best job. So hopefully this is working for a lot of people, as best as it can. Let's go through this example. Let's remove 32 together. Again, I just want to remind everyone I will be uploading this, so not too big a deal. So I want to remove 32. There's no one sitting next to you, and you can just talk it out on your own. I want to remove a 32, then a 5, then 10, and finally 15. But you have to use this algorithm we just worked through, right? So just what I don't want you to do is like rearrange the tree in other ways. You want to do it the way we just kind of saw in our algorithm. So let's go first. So if I want to get rid of that 32, I have to go to the left subtree, find the largest value. Well, that's 25. So that makes life easier. Basically, this becomes, maybe I use a different color for that just to kind of indicate that it's been overwritten. There we go. Then I want to remove a 5. Well, it has no children, so it's easy to get rid of it. How about 10? At this point, 10 doesn't have that 5, so we're done. Finally, the 15. 15 is that situation, that first part of part 4, where the left child is null. There is no left subtree at this point. So then 16 becomes the new root. So this goes away. We end up making this 16. So if we want to see what the final tree looks like after, it's a 20, 16, 25, 45. This is like totally what you might see on your final exam, like a question like this. And you might have different trees as your final answer, and it'd be multiple choice. And guess what? That final tree would all have those 4 numbers. Only one of them would be in this exact sequence, though, the correct sequence. Let's work through another one. Let's remove the 20, the 32, and then the 10. Okay, so 20. The rules are you got to look in the left subtree. So I'm going to be looking in here for the largest value, and it's this 16, right? Because we'd go left and then drill right till we found the largest one, 16. So the 16 would go away, and it would overwrite that 20. So in essence, removing the 20. Then I would want to remove the 32. 32, largest value over there is this 25. So this 25 would go away. And then we would be left with a 25 there. Finally, I would remove my 10. Go to the left subtree, find the largest value. Well, there's only a 5, so that's the 5 that gets copied into that 10 and then deleted. So what's the final tree look like? I would want to see 16, 15, 5, 25, and 45. Kind of funny and interesting looking, right? It's basically not even a tree anymore. It's more of a linear structure. And you could actually get very, very linear stuff. I'll talk about that in a couple more slides. Okay. But what I want to do now is I want to show you the insert code. So we're not going to work too much through this. We've kind of already discussed how insert should work. But here you go. If it's the first node you're inserting, the if statement takes care of that. You create a new node and the root pointer points to this new node. Otherwise, you call on helper insert to help you find the correct location. It basically finds the parent of where this new node's going to go. So it tells you where the location, and then you check. If it's less than or equal to, make it its left. If it's otherwise greater than, you make it its right. Helper insert, it's basically working like a search. Okay? So keeping in mind, you have to write a search function for BST. So this code here is essentially already searching for a value. So you're probably going to be able to use a lot of this code to finish writing the search function. Okay. But so if the root is a leaf, then you return the root because it's going to either go on the left or to the right. Otherwise, if your target is less than the root data and the root left is null, well, that's where it belongs because there's nothing else to go down. Similarly for the right side. But otherwise, if the target is less than the root data, then you have to drill down left. If it's greater than, you go right. So go through this code, kind of draw it out, trace it out, make sure it makes sense. Maybe I can help with these 3 here, though. I do have a couple of drawings here on my notes to help you visualize that, why those return the root where the other ones have to drill down. What this first one here is saying is you arrive at a node, and this is, actually no, this is null, and this is null. Therefore, your new node is either going to go here or here, and there's no more recursion to be done. There's no more nodes to look through, so I'm able to say, okay, return the address of that. Over here with the second, first else if, what we're saying is this is null. This might have a lot of stuff, but guess what? I know this value has to go on the left because it's less than or equal to the root data. Therefore, I'm ready to say you're going to attach it to this thing, right? Over here is the opposite case. The left is, who knows how big the left is, but the important thing is it goes on the right, and the right is already null. It's already empty, so there's a spot there for that node to go. And then again, the else if else that come after this are the recursive calls to find what you need. So here's a little main that you'll be able to test stuff with. There's also another main in the lab. But here's our final closing thoughts. Best case scenario, if we can guarantee we have a balanced binary search tree, then these functions essentially have an O login average runtime for search, for insert, for remove. excellent, excellent runtime. Um, as it scales up, the runtime doesn't go up by very much. But we need to have a balanced tree in order to do that. So that's going to be another lecture. Worst case scenario, the BST looks like a linked list, and then all of these collapse to ON, so it becomes linear. You might ask yourself, Mr. C, how is that possible? Let me show you what a worst case might look like. Let's say someone insert a 10, then an 8, then a 5, then a 2, and then a 1. Maybe you've already caught on, but check it out. So first we say 10, and then an 8. Oh, so that goes there. And then a 5. Oh, that 5 goes there. Oh, and then a 2. Oh, and then a 1. Oh, and here's our root pointer. What's that? That's a linked list, right? That's a linear data structure. We're not taking advantage of the tree's branching in order to optimize some of these functions. So it will be important to learn how to balance these trees in another lecture. All right. Okay, everyone. This has been a fun lecture. I will talk to you again soon. Have a good week.